8:30. Hello guys, good evening. Hello guys, are you there? Can you see the screen now? Good evening guys, who all are there? Please type in your name. Please type in your name in the chat box. Can you see the screen now? Hello Anirudh. Hello Aditya. All of you can see the screen. Can we start now? Okay. So guys, we are going to start today optical isomerism. Okay, and probably in this 2-hour session we'll finish optical isomerism, right? So first of all, you see optical isomerism is what, right? How do we define the phenomenon called optical isomerism, right? So the optical isomerism is actually the behavior of a molecule towards plane polarized light. Okay, how a molecule can behave towards plane polarized light. What is plane polarized light? That also we'll see. Okay, if the behavior of the molecule towards plane polarized light we observe. Okay, if the molecule can rotate the plane polarized light in any direction, whether it is clockwise or anti-clockwise, if the rotation is possible, it means that the molecule is optically active. Okay, what is optically active molecule? All those molecules which can rotate the plane polarized light in any direction, right? That we call it as optically active compound. When the when there is no deflection in plane polarized light, when there is no deflection, when there is no rotation, then the molecule is said to be optically inactive. Okay. So this is what, like, now when I say the behavior of a molecule towards plane polarized light. Okay. Obviously, this from this you won't understand like what is PPL, what is behavior, what we are talking about actually. Okay. But the basic definition of optically active compound is the compound which can rotate plane polarized light in any direction, called optically active. Okay. So now we'll start with the definition of optical isomerism. Okay. So optical isomerism is defined as the compounds having, all of you write down, the compounds having having similar physical and chemical properties, similar physical and chemical properties, compounds having similar physical and chemical properties, but their behavior towards plane polarized light, but their behavior not working, behavior towards plane polarized light plane polarized light towards plane polarized light is different towards plane polarized light is different are called optical isomers, optical isomers. And this phenomenon is and this phenomenon is optical isomerism. Optical isomerism. Optical isomerism. Yeah, hi everyone. Siddharth, Nikita, Shaunak, Pradeep, Shreya. Okay. So the behavior or the definition of optical isomerism is what? Compounds having same physical and chemical properties, but behavior towards plane polarized light is different, are called optical isomers, and this phenomenon is optical isomerism. Okay. Now, what is plane polarized light? Right. So first of all, we'll see what is plane polarized light that we are discussing. What is plane polarized light? Okay. Light, you see, when you have a light source, okay, suppose you'll have a light source, that light source will emit light in all direction actually. This direction, this direction, every possible direction, the light source emits light like this. Okay. So what we do, this is a white light. Okay. Light source which emits white light basically. White light. Okay. Now this light we allow to pass through a prism that we call it as Nicol prism. This is Nicol prism. Nicol prism. Okay. My pen tablet is not working. I don't know. I have to see the settings. Anyways, mine is particular. Nicol prism, right? Now, when this light passes through this plane Nicol prism, all the lights, right? Uh, we can say polarized in one direction, which is not exactly true. Why? I'll tell you. But when the light passes through the plane polarized light, we get the light which is parallel to each other, or all the lights are there in one plane, right? You see here, here the lights are in all the direction, but here the lights are in one direction, okay, along a same plane. All the lights along a same plane. So what you can understand, hello Chirag, hello Arya. So what is the meaning of this? You can understand actually in Nicol prism, there is, in Nicol prism, there is a slit, very ultra fine slits present in the Nicol prism, right? Ultra fine slits present in the Nicol prism, like this. We have very fine slits present in the Nicol prism. All those lights which are parallel to these slits, okay, basically slits means we have a gap in between, right? So suppose the lights are going in this direction, we have horizontal light, suppose we have. So that horizontal light will, collide with this bar that you have over here and reflects back, or will reflect in the other direction. Only those lights which are parallel to these slits will pass through the slit, and hence, like, on the other side of the prism we'll get the light which is parallel to each other. Okay. And this light we call it as plane polarized light, because all the lights are in one plane, so we call it as plane polarized light. In short, we call it as PPL. Okay. Now what we have to do here, the organic compound which whose behavior you have to understand whether it is optically active or not. Now this plane polarized light, we allow this light to pass through the organic compound, whatever organic compound we have. We allow this light to pass through the organic compound. Suppose this is the organic compound we have. Right. When this light passes through the organic compound, so there are three possible observation we may have, right? One observation is what? The light will deflect, and the deflection of light may be in clockwise direction, like this, or it may be in anti-clockwise direction. This is one type of behavior. And other behavior is what? There is no deflection in the light at all. The light comes out from the organic compound as it went into the organic compound. Right? There's no deflection in the organic compound. So when there is no deflection, like in this case, the given organic compound is said to be optically inactive. Optically inactive. When there is no deflection, it is optically inactive. When the light deflects in any direction, it is optically active. OA in short, I am writing it down. Got it? Any doubt? Let me know. If you have any doubt, let me know. Till here, any doubt? Any doubt? Shreya, Pradeep, Aditya, Anirudh, Siddharth, Shaunak, Chirag, Arya, Nikita. Any doubt? Let me know till here. Right. So behavior of light towards plane polarized light we are observing. Right. Now the assumption is what? If the PPL, that is plane polarized light, if the PPL rotates rotates clockwise or towards right, the PPL rotates clockwise, the compound is said to be dextrorotatory. Compound is said to be dextrorotatory, or in short we call it as D, only D, small d. Or we also write it as plus. Plus means dextrorotatory, D, clockwise rotation. Okay. When PPL rotates clockwise, it is dextrorotatory, small d or plus. If the PPL rotates anti-clockwise, it is called it as levorotatory. Laevo. Levorotatory, that is small l, or we call it as minus. All these are experimental thing, plus and minus. If I give you a compound and ask you whether it is dextro or revo, you have to perform this experiment. You have to perform this experiment, and then you have to check whether the light is rotating clockwise or anti-clockwise. Then only you can say it is dextro or levo. Listen to me very carefully here, that dextro and levorotatory compounds is experimental. There is no theoretical way so that we can say that the given compound is dextro or levo or plus or minus. Okay, there is no theoretical way. Now, suppose if I give you one compound, or if you get a question in the exam, and the question is the given compound is optically active, yes or no, right? Then what you have to do? Till now, we haven't seen any theoretical method, right, to understand whether a given compound is optically active or not. You have to perform this experiment, and you have to see or observe the deflection in PPL. If yes, deflection is there, then it is optically active, otherwise inactive. So obviously, this method you cannot use in the exam. You cannot, no, the examiner will not give you that compound. It is in the question paper, right? You don't have all those facilities so that you can perform this experiment. So obviously, there must be a theoretical way to find out the compound, whether it is optically active or not. All these are experimental. Again, I am repeating, for a given compound D and L, there is no other way to find out, but there is no other theoretical way to find out D and L nature of any compound, right? In the book, for some compounds, it is written, it is dextro, it is levo. That is based on this experiment. Okay, so we are not going to perform this experiment in the exam. So we must have some other way or theoretical way to find out the optical active nature of a compound. So we are moving towards that theoretical method, right? So before doing all those before understand all those methods, there are few terms we have to understand. Okay, and all these terms are very important. Okay, all of you understand it carefully. The first term we are going to understand here is chiral center. Write down chiral center. Okay, I'll dictate, guys. All of you write down definitions and everything in your notebook. Okay. See, my this pen tablet is not working smoothly, so I am just struggling a bit. Okay, that's why I'm trying to dictate you. Otherwise, I would have, written things on the screen. Whatever is important, urgent, that I'll definitely write. But when I'm dictating, you must write it down. Now, the definition of chiral center is what? Write down, all of you. An sp3 hybridized atom, an sp3 hybridized atom having four different atoms or groups attached to it. An sp3 hybridized atom having four different atoms or groups attached to it is called chiral center. Right? So chiral center, the condition is what? It must be sp3 hybridized. And when sp3 hybridized, the geometry is tetrahedral, right? For suppose if I write down this molecule, carbon has OH, H, then we have suppose CH3, CH3, and one more atom is suppose deuterium is attached to it. Okay, now when I talk about this carbon, first of all, the condition is what? The carbon must be or the atom must be sp3 hybridized. So this carbon atom is, yeah, it is sp3 hybridized, and there are four different atoms or groups attached with it: OH, H, CH3, and D. Since there are four different atoms or groups attached to it, this carbon is chiral carbon. And chiral carbon we denote by star. Right? Star mark means this carbon is the chiral carbon. Right? So any center or any atom which is sp3 hybridized having four different atoms or groups attached to it is called chiral center or chiral atom. If carbon is that atom, then we call it as chiral carbon. Write down this point. If carbon is the atom, then we call it as chiral carbon. Then we call it as chiral carbon. Okay. One very important note we have here. All of you write down this note. All of you write down this note. Write down presence or absence of chiral center. Presence or absence of chiral center. Presence or absence of chiral center is not any criteria. Absence of chiral center is not any criteria for a molecule to be optically active. Presence or absence of chiral center is not any criteria for a molecule to be optically active. Right? Next line. But if the molecule has only one chiral center, then it is said to be optically active. But when the molecule has only one chiral center, then it is said to be optically active. Did you understand this point? For a given molecule, if you have to find out whether it is optically active or not, right, then presence or absence of chiral center is not the criteria, right? But if you find out that, or if you see that there is only one chiral center in the molecule, then you can say that the molecule is optically active. Okay? Molecule is optically active. But still, we have an example where there is no chiral carbon or chiral atom present, then also the molecule is optically active. Okay, we have that example also. That's why I am saying that presence or absence of chiral center is not any criteria for a molecule to be optically active. Right? Right. What observation we have, that if the molecule has only one chiral center, then it is optically active. This is our observation. It is not the condition. It is not the criteria. Chiral center is not the criteria for a molecule to be optically active. Very important point, this one. Okay. Now in this, we have one exception also. Write down the exception. And what is that exception you see? Tertiary amines. Tertiary amines are what? When the nitrogen has three alkyl group attached. And I am taking three different alkyl group. R1, R2, R3. And apart from these three alkyl group, we'll have one lone pair also present onto the nitrogen atom. Lone pair on nitrogen atom. So you see this nitrogen atom is also sp3 hybridized. Four different groups are there: R1, R2, R3, and a lone pair, right? So according to the definition of optical activity, if the molecule has only one chiral center, it is optically active. So according to that logic, you see this molecule should also be optically active because it has only one chiral center, which is the nitrogen here, right? And four different groups attached. But this molecule or tertiary amine is optically inactive. It is an exception. Tertiary amine is optically inactive. Inactive. This is an exception we have. Got it? Is it clear, guys? Is it clear, guys? Let me know. Any doubt, any confusion? You can write your doubt over here. Okay. Okay. Now, can you tell me how many chiral center are present in this molecule? If present, then bromine. Question number one. Do we have any chiral center present here? How many chiral center we have in these two molecules? Tell me, this is first and this is second. Do we have chiral center in first compound? First compound, we do not have any chiral center. Okay. Now you see this. This carbon is sp3, fine, but we have 3 hydrogen present, so it cannot be chiral carbon, right? Condition is what? sp3 hybridized and 4 different atoms are grouped, right? So this is sp3, but we have 2 hydrogen here, 3 hydrogen here, not possible. This carbon is also sp3, but 3 hydrogen here, not possible. But when you see this carbon atom, it has here, it has 1 hydrogen present here, right? It has 1 hydrogen present here, and one group is this ethyl group. This whole group is ethyl group. Another group is methyl group. Other one is hydrogen, and other one is bromine. So yes, carbon is sp3 hybridized, and we have 4 different groups attached. Hence, this carbon is the chiral carbon, right? Only one chiral carbon we have. This carbon you see in the ring, we cannot have chiral carbon because all the carbon atoms are sp2 hybridized. Okay, sp2 hybridized carbon or any atom can never be chiral center or chiral atom because the condition is the atom must be sp3 hybridized. Okay, so this carbon you see, yes, this carbon is sp3 hybridized, but since it contains 2 hydrogen atom, so it is also not a chiral carbon. This carbon is again an sp3 carbon, and it has 4 different groups attached to it. One is cs3, other one is h, then cl, and other one is the whole group. So yeah, this carbon is a chiral carbon, and we have 1 chiral carbon also present in this compound. Got it? Understood? Now see, like I discussed and said, that presence or absence of chiral center is not any criteria for a molecule to be optically active. Then what is the criteria and condition for a molecule to show optical activity, right? So that condition or that criteria is chirality. Next heading you write down. Chirality or chiral molecule. No, Aditya. Second carbon from the left, you are talking about this carbon. Okay? You are talking about this carbon. This carbon is sp3 hybridized, but it contains 2 hydrogen atoms. Since 2 hydrogen atom we have, that's why it is not an chiral carbon, because we must have different atoms or groups attached to it. That is the condition. So this carbon is not chiral carbon. Got it? Got it, guys? Yeah. Now the condition for a molecule to show optical activity is chirality or chiral molecule. One thing you always keep in mind, that this chirality has nothing to do with chiral center. Okay, chiral center is different, chirality is different. Okay, both are not at all same, or they have nothing to do with each other. The both term has nothing to do with each other, right? The first point in this you write down: any molecule which can not be divided into two equal half, any molecule which cannot be divided into two equal half, is called chiral molecule. Is called chiral molecule. Chirality is the property of a molecule. Chirality is the property of a molecule by which it cannot be divided into two equal halves. Wrote. Chirality is the property of a molecule by which it cannot be divided into two equal halves. Next line. Chirality and chiral center. Chirality and chiral center are two different terms and they have nothing to do with each other. And they have nothing to do with each other. Always keep this in mind, that chiral center and chirality are not at all same. They are completely different from each other. Right? Next line. Chirality, if the molecule is not symmetric. Yeah, right. I'm coming to that, Anirudh. I'm coming to that. Just give me a few more minutes. I'm coming to that point. Next point you write down. Chirality is the main criteria comma, necessary and sufficient condition. Chirality is the main criteria, comma, necessary and sufficient condition for a molecule to be optically active. Next line. If the molecule is chiral, it does not mean that it has a chiral center. Not necessary. If the molecule is chiral, it does not mean that it has a chiral center. Right? Chiral molecules next line. Chiral molecules are non-superimposable to their mirror image. Chiral molecules are non-superimposable to their mirror image. Superimposability, you write down the definition next line. Superimposability is a 3D phenomenon Superimposability is a 3D phenomenon. If two molecules are superimposable, if two molecules are superimposable, and if we place one molecule onto another, two molecules are superimposable, and if we place one molecule onto another, it looks like a single molecule. Right? All these 4-5 points that I've given you, all these points are very important. Okay? Now, again, I'm telling you the necessary and sufficient condition for a molecule to be optically active, that it should be chiral in nature. Now, what is chiral? Chiral molecule are those molecules in which there is no kind of symmetry. If there is any kind of symmetry present, then the molecule cannot be chiral and it won't be optically active. How do we decide that the molecule is chiral in nature? We have to check the plane of symmetry or center of symmetry. How to check that? That also we'll see with some example. But to decide for a given molecule is chiral or not, we'll check what kind of symmetry we have, if it is there. If the symmetry is not there, any kind of, mainly plane of symmetry and center of symmetry, if the symmetry is not there, then the molecule is chiral and it is optically active. If any kind of symmetry is present, then the molecule is said to be achiral. Write it down. If there is any kind of symmetry, if there is any kind of symmetry present in the molecule, if there is any kind of symmetry present in the molecule, then it is said to be achiral. Then it is said to be achiral and it is optically inactive. It is said to be achiral and it is optically inactive. One last line in this. If the molecule has only one chiral center, if the molecule has only one chiral center, it is optically active. Only one chiral center, optically active. Remember, if you have 2-3 chiral center present, then we cannot say whether it is optically active or not. If only one chiral center, it is optically active. Having said that, presence or absence of chiral center is not any criteria, must keep in mind. The only criteria for a molecule to be optically active is chirality. The molecule must be chiral molecule. How do we decide chirality? There should not be any kind of symmetry present in the molecule. When I say symmetry, means there should not be any plane of symmetry or center of symmetry. How to do that? We'll discuss. Okay. Now there is one more term, and then we'll move on to, you know, to discuss or to understand if the given molecule is optically active or not. Okay. There is one more term you write down, and that is stereocenter. Stereocenter. Last class also I have given you the definition of it. Why I am, discussing this is here also, because we should know the difference between stereocenter and chiral center. Any doubt till here? Anirudh, Shreya, Aditya, Arya, Tridev, Nikita, Siddharth. Any doubt? Tell me. Till here, is it clear? Okay. Now, next write down stereocenter, like I discussed in the last class. It is a double bond or ring or chiral center. It is a double bond or ring or chiral center due to which it is a double bond or ring or chiral center due to which stereoisomerism due to which stereoisomerism is possible. Okay. Stereo center, stereogenic center, all are same thing, both are same thing, right? It is a double bond or ring or chiral center due to which stereoisomerism is possible. One very important point next when you write down, stereocenter may be sp2 or sp3 hybridized. Stereo excuse me. Stereocenter may be sp2 or sp3 hybridized. Okay, so you see, chiral center is what? The hybridization of chiral center is always sp3, but stereocenter can be sp2 or sp3, right? So what we can conclude from this, that all chiral centers are stereocenter. Write down, all chiral centers are stereocenter, but the converse of this is not true. But the converse of this is not true. Got it? This is the difference between stereocenter and chiral center. Stereocenter can be sp2 also, but chiral center cannot be sp2. It is always sp3. Okay. Now you see this molecule. Tell me, do we have any chiral center in this? CH3. Tell me, in the first one, do we have chiral center present? In the first one, yes, we have Chiral Center in the first one, because you see, first of all, we have to check, or we have to find sp3 hybridized carbon. Okay, so yes, this carbon is sp3 hybridized, right? This carbon is sp3 hybridized with chlorine and hydrogen, two different atoms we have here. Now we have to decide what are the other two groups attached with this carbon, right? So for that, what we have to do, we have to go clockwise and anti-clockwise, right? If the paths are same, the path is same in both direction, it means the same atoms or groups attached with that carbon. If the path is different, it means we have different groups attached, right? So when you go in this direction, you see we have carbon-carbon double bond, but such carbon-carbon double bond is not present here, right? It means this way and this way the path is different, and hence two different groups attached with this carbon atom, and hence this carbon atom is the chiral carbon, right? Similarly, here both paths, here the both of the paths is same, right? So there is no chiral carbon in this compound, only one chiral carbon present here. And since we have only one chiral carbon present, optically active this compound will be, since only one chiral carbon is present. Okay. For any molecule, if you have to decide whether it is optically active or not, you can go through with presence or absence of chiral center. If there is only one chiral center, yes, optically active. If there is no chiral center, we cannot say whether it is optically active or not. If more than one chiral center, then also we cannot say whether it is optically active or not. Okay. In that case, when we have more than one chiral center or there is no chiral center, in these two cases, what we have to do, we have to check chirality, whether the molecule is chiral or not. Okay. And how do we check chirality? We'll check plane of symmetry or center of symmetry. Any kind of symmetry will check. Got it? So Stereocenter is this. Now we have a representation of molecule. Okay. Write down the heading, representation of molecule. Representation of molecule. Now you see D and L configuration are experimental, correct? I told this in the beginning only. D and L are experimental, right? Then what is the theoretical way to find out the behavior of a molecule towards ppl? That is chirality, we have discussed. Now, one compound can rotate the plane if it is optically active, can rotate the plane polarized light in clockwise direction, and one can rotate in anti-clockwise direction, right? So how do we know that the given compound rotates clockwise or anti-clockwise? That is what we are going to understand now. Okay, and what do we do for that? Means the behavior is to behavior towards ppl, how the molecule behaves towards ppl, whether it rotates clockwise or anti-clockwise. How do we understand that? That we are going to understand now. And for that, you should know one or two representation of molecule. How the molecule represent? How do we write down the structure of a molecule? Okay. So there are two representation we have that we are going to discuss here. The one is flying wedge representation. The first one you write down, flying wedge. You must know this. Flying wedge. We also call it as wedge dash representation. Flying wedge representation. And the other one is Fischer. Fischer projection. Fischer projection. These two we have to discuss. Now you see flying wedge representation is what? Suppose we have a molecule, right, carbon, and it is attached with four different atoms or groups. Suppose OH we have, and it is also attached with this is dash actually. Hydrogen. Then we have chlorine, and then we have deuterium. Right? So this dark wedge, we call it as dark wedge is this, and this is what? This is the dash, wedge dash representation. You must have seen this kind of bond, like which is connected with the, you know, the dot line, and one kind of bond which is connected with this, the thick line, which is this kind of bond you must have seen. Okay, so what is the meaning of these two bonds actually? This bond, which is represented by the dark wedge, it is coming towards the observer. It means what? You see, I am looking at this molecule, I am looking towards my screen. Okay, you are also looking towards your screen. So this carbon OH bond is coming towards me, or it's coming towards you. It is coming out of the screen towards you, right? So this dark wedge means the bond is coming towards the observer, right? So write down this. Dark wedge means this kind of wedge means the bond is coming towards the observer. Dark wedge means, you write down, the bond is towards the observer, and the dash representation that we have, it means the bond is going into the plane. Means this hydrogen, which is connected with a dash bond here, right? It is going away from me. It is going away from you, right? Into the plane of the paper, or into the plane of this, right? So this is the meaning of flying wedge representation. Okay, flying wedge representation. Got it? Flying wedge. Any doubt in this? Flying wedge. Any doubt? Guys, tell me, any doubt? Flying wedge? Dash bond means away from the observer. Dark wedge means towards the observer. That is it. Okay. Now, Fischer projection is what? You must have seen this kind of structure, like this. Oh, wait. Like the structure of glucose, I'll draw here. You must have seen this kind of bond, no? Horizontal bonds, like this. Okay, where we have here CHO present, OH, then H, OH, like this structure. The point is, you must have seen this kind of structure, whether we have two chiral center or one, this kind of structure you must have seen, right? So this representation is Fischer projection, first of all. The cross representation we have is Fischer projection. Now, what is the meaning of Fischer projection? Okay, so first of all, you see, if I take one example, this one, suppose here we have CH2OH. This is hydrogen. This is chlorine. And this is methyl, CH3. Do we have any chiral center in this molecule? Do we have any chiral center in this molecule? Yes, the center one, right? This is the chiral center, right? This is the chiral center, and we have only one chiral center, right? That's what the thing we have. Now, what is the meaning of this Fischer projection? In Fischer projection, what happens? The horizontal bond, this bond, is coming towards the observer. Horizontal bond, write down the 2 points here in Fischer projection. Horizontal bond is coming towards the observer, and vertical bond is going away from the observer into the plane. And vertical bond is going away from the observer into the plane. The horizontal bond is what? It is coming towards the observer. Horizontal bond is coming towards the observer out of the plane, and vertical bond is going into the plane of the into the plane away from the observer. Okay. So now, if I represent the three-dimensional view of this molecule for a better picture, what we'll write, since the horizontal bond is coming towards the observer, means this bond we must write with a dark wedge like this. Okay, this is CH2OH. This is CH3. CH3. This is chlorine, and this is hydrogen. Okay, just a second. Huh? कल कल लेना है ना अच्छा बाइक से आए हैं करते कुछ वर्क कर लेंगे आप ठीक है okay did you understand this did you understand guys that's what we are representing Shreya the vertical line is into the plane that's why the dash line and horizontal line coming out of the plane is that's what the dark wedge that we have okay so you can imagine a V shape okay that which is coming towards you and another V that is going away from you like that the open end okay so that's the thing I can explain in the class but I think you can understand from this any one of you have doubt here Fischer and all why in the plane because carbon is sp3 no which one is coplanar here which one is there's no planar the carbon atom is sp3 hybridized the molecule is not at all planar the mutual bond angle is 109 degree got it the mutual bond angle is 109 degree the atoms or groups in Fischer projection when we have only one sp3 hybridized carbon it's not at all planar they are in different plane what Nikita I didn't get What about those not going away or towards? See, first of all, this is this molecule. This molecule, you see, it looks like planar. This molecule, when you look at the structure like this, it looks like planar in a plane, Fischer. But actual thing or actual representation is this. It is not at all planar. These two atoms or groups, which is on the horizontal line, is actually coming towards you, right? And these two atoms or groups, which is on the vertical line, it is going away from you into the screen. We have only four groups here, Nikita. Two is coming towards us and two is going away from us. Only four we have. This you let it be. Flying wedge, you let it be. You don't compare this and this now. First, you try to understand this, Fischer. Flying wedge is this. Got it? So these 2 points you must keep in mind. Fischer projection looks like planar because we draw like this. We draw across like this. Okay? But it is not at all planar. Understood? Understood, guys? Tell me. Any doubt? Can we move on? Can we move ahead? Okay. Now you see, like I said, that the molecule, the behavior of a molecule can either be D or L, dextro or levo. But dextro or levo, wedge dash representation, yes, we show that to bond, but it is not planar. It is actually, uh, you know, see, there are only two things we can say. One is going towards away from us, and other one is coming towards us, right? This is only two possibilities. So it's flying wedge, we only represent these two, and other two we say that it is in a different plane, not in the plane of these two. That's the meaning. Okay, these two are in different plane, these two will be in different plane. But since we have only two possibilities, we can show one is coming away from us and one is going away from, and one is going away from us and one is coming towards us. There's no other third, there's no other possibility away and towards us. That's what we can say. So in flying wedge, other two bonds are not in the same plane, but when I say it is not, it is planar, it does not mean that these two are in the same plane. The point is, the plane of this and these two will be different. And these two will also not be in the same plane. It's a very simple logic. The bond angle between these two is 109 degree. Right? So it is tetrahedral. It cannot be in the same plane. For the molecule to be in the same plane, they must be linear, 180 degree. Right? Now you see, like I said, D and L representation or configuration of a molecule is experimental, right? To find D and L, you have to perform that experiment, the first one that I discussed, correct? But that we cannot do in the exam. So we have different terms which we use to define the behavior of a molecule towards plane polarized light, and those terms we call it as R and S configuration. So RS configuration we can find out theoretically. D and L is experimentally we cannot find it out. We have to perform that experiment. So whenever you get the question in the exam, you have to find out R or S configuration. Correct? So how to find out R and S configuration? That you write down. Write down the heading RS configuration. Heading write down RS configuration. Okay, so in this you see uh, we have one rule actually, one condition we have to apply, and that is it. Just a second. Hello. नहीं sir, my bike's नहीं bike. Okay, so RS configuration we have to understand. Okay, so there are actually two things. Okay, so in Fischer projection what we do, and in West dash representation what we have to do, right? So first of all we see we can also convert Fischer into wedge dash, and vice versa also. Means conversion is possible. We can convert Fischer projection into wedge dash, or wedge dash into Fischer. Okay, so that conversion we won't understand now. That we'll do in the class. Okay, that will be, physical class will be better for you to understand. So that conversion we are skipping now. Okay, what constraint we have, and what we have to, how we have to, assign RS configuration in both type of projection, that we'll understand today. Okay, now suppose the molecule is this. Uh, the molecule I am taking is this carbon. With this carbon we have chlorine. This is chlorine, and this is hydrogen. And here we have CH3, and here we have bromine. This is the molecule. So obviously the molecule is optically active because it has only one chiral center. Right? Now to assign RS configuration in this wedge dash representation, the condition is what? Oh, first of all, the first step one, write down, is to assign priority. Assign priority to the atoms or groups attached to priority to the atoms or groups attached to the chiral carbon. The chiral carbon or chiral atom. Now the condition in Fischer projection is what? Write down the condition. Condition you write down. In wedge dash representation. In wedge dash representation, the least priority group must be into the plane. Must be into the plane. The least priority group must be into the plane. That's the condition, right? The group or atom which has the least priority, that must be with this dash bond. That's the condition we have, right? Now the third point is what? We have to go, or we have to trace this line. Trace the circle, you write down. Trace the circle. And how do we trace the circle? We have to go from first priority group to the third priority group. First to third via 2. Right? First to third via 2. We have to complete the circle like this. Condition is what? The least priority group must be on the bottom of the. Yes. Correct, Anirudh. Priority will assign according to CIP rule. Okay, will assign the priority. The least priority must be going into the plane. I'm talking about which dash now. Fischer Projection will discuss. Okay, in which dash the least priority group must be into the plane. Then we have to trace the circle. We have to go from first priority to third priority via second. What are CIP rules, Shreya? We are not going to discuss here. Last class I have discussed. You go through the notes. If not, then you can ask me personally. I'll tell you. Right? For CIP rule, again, there are 5, 6 rules. So I cannot dictate all those. Only thing is what? Here, actually, here I'll tell you how to assign priority. Atomic number you have to compare. But I'll suggest you to write down the rules from your friend's notes. Right? So, condition is I have given you first to third via 2. Now you see, to assign RS configuration, the fourth thing is what? If this circle is clockwise, right? If this circle is clockwise, then the configuration is R. If it is anti-clockwise, then the configuration is S. Got it? If it is clockwise, configuration is R. Anti-clockwise configuration is S. Now you see we are going to assign the configuration of this molecule. Correct? First of all, we have to assign priority. Shreya, priority will assign by the comparison of atomic number. Okay, so we'll compare the atomic number of all these elements. If the groups are attached, then we compare the atomic number of first atom. Here it is carbon, right? So which one has the highest atomic number? Obviously bromine. So bromine has the highest priority. Then we have chlorine second. Then we have carbon third. And in the last we have hydrogen fourth. That is what the condition we have. If the least priority group must be into the plane of the paper, right? So it is already there. If it is not there, then what we have to do, that also we'll see. Don't think about that now. Okay, what we have to do, we have to go first to third priority via second, right? Like this we have to go. So when you see this circle is what? It is clockwise, correct? It is clockwise. Clockwise configuration is R. So this compound has R configuration. Any doubt, guys? Let me know, guys, if you have any doubt fast. Is it clear? All of you understood? Where is Trideep? Okay. What I did, first of all, I assigned priority 1, 2, 3, 4. Then what we have to do, we have to go from 1 to 2, 2, 3, right? This is the condition we have. So from first priority to third priority group, I have to go via 2, right? Since via 2 condition we have, so we cannot go like this, right? So first, then second, and then third. This rotation you see, this rotation is what? It is clockwise. So when it is clockwise, it is R. Okay. No, RS and plus minus again we cannot say, Anirudh. Plus minus, like I said, it is experimental. DL, what I said, it is experimental. The one which is D, that must be plus. The one which is L, that must be minus. Okay. Yeah, that's what. So plus and minus, we cannot say by looking at the molecule. There is no theoretical method to find out plus or minus configuration. Don't worry with that. Plus and minus, they are not going to ask. They will ask you in the exam the configuration, whether it is R or S. No, it does matter. That's the condition, Shreya. The fourth priority group must be into the plane of the paper. Must be into the plane. That's the condition I have given you for flying wedge representation or wedge dash representation. Got it? Now I assume that all of you have written this part, right? So I'll just erase this first. Now you see, very important, point we are going to conclude here. Now you see, in this molecule where configuration we have already known, which is R, we have concluded that. Now what we are doing, I am just swapping chlorine and CH3, right? Swap Cl and CH3. What we get, you see, we have carbon, chlorine is coming towards the observer, which is swapped by CH3. So now this CH3 is coming towards the observer, towards us, and chlorine is here, bromine is here, and we have hydrogen present here, right? No, that's the only representation. It should be into the plane of the paper, right? Whether you write between bromine and CH3 or bromine or chlorine or CH3 or chlorine, that does not make any difference. It should be into the plane. That is it. Right? So now when you exchange one pair or when you swap CH3 and Cl, then what happens? Again, what we have to do? Again, we have to assign the priority. So we'll assign the priority first. Bromine is 1, chlorine is 2, methyl is 3, and hydrogen is 4. Since the least priority is into the plane, so fine, that's what the condition we have to follow. That's what the condition we have to follow, right? So we have to go from 1 to 3rd via 2. So this is the rotation we have, and this rotation is what? This rotation is anti-clockwise, and anti-clockwise is S configuration. Got it? Got it? Now, next is what? Again, we are swapping chlorine and bromine, suppose. Swap chlorine and bromine. When we swap chlorine and bromine, what we get, you see, carbon has CH3 as it is, CH3 as it is. Here we have bromine, here we have chlorine, and hydrogen we have here. Again, what we do, we'll assign the priority. So priority is 1 here, 2, 3, 4. 1, 2, 3 via 2. So like this we have to go. Now you see it is clockwise. So clockwise is what? R. It's R configuration. How many of you understood this? How many of you? Quickly you tell me. It's already 8. We have half an hour more. Fischer also I have to discuss. Nikita, understood? Okay. Okay. Wait, Anirudh. So what you can observe from these three examples? You see, initially the configuration is R, correct? When we swap one pair, when we swap one pair, the configuration becomes S. Again, if you swap one pair from here, the configuration becomes R, right? But when you compare this first and third molecule you compare, they have same configuration, right? And to get third from first, what you have to do, you have to exchange, first of all, you have to exchange CS3 and Cl, and then a Cl and Br. Means when you have to form third from first, you have to swap two pair, right? One is CH3, CH3 and Cl you have to swap first, and then you have to swap what? Cl and Br, correct? Right? Now, next, what we can say, if you have two pair, if you swap two pair, then the configuration remains same. If you swap one pair, then the configuration change from R to S and S to R, right? So how we can generalize this? We can say when we have odd number of exchange, means the exchange number is odd, then the configuration changes from R to S and S to R. But if you have even number of exchange, even number of swap, then the configuration won't change. Did you get this? Right? So write down this point. If you have odd number of exchange, if you have odd number of exchange, the configuration changes from R to S or S to R. This is very important point. When the configuration changes from R to S or S to R, did you write this point? When there is odd number of exchange, the configuration changes from R to S and S to R. Next point, if we have even number of exchange, like 2 pair, 4 pair, 6 pair, if we are getting exchanged, if we have even number of exchange, then the configuration remains same. It won't change. Is it clear? Did you understand this? Even number of exchange, no change in configuration, it remains same. Odd number of exchange, the configuration changes from R to S or S to R. Is it clear, all of you? Tell me fast. Correct? Now you see, in all these molecules, first, second, and third, the least priority is into the plane of the paper. Right? So what we do, what we will do when the least priority is not into the plane of the paper. Like suppose if I write this example, carbon is attached with chlorine. Here we have hydrogen. Here we have CH3. And here we have bromine. Can you tell me the configuration of this? What is the configuration of this molecule? The only condition for least priority group is it must be into the plane of the paper. That is it. That's the only thing you have to keep in mind. Odd number of swap, configuration changes. Even number, configuration won't change. Correct, Aditya. Tell me the answer. See, here what we do, when we assign the priority, okay, when we assign the priority, this will be 1, this will be 2, this is 3, and this is 4. Now the condition for flying wedge representation is what? The least priority must be into the plane of the paper, which is not here, right? Which is not here. So what we have to do here, this H or the least priority will swap with the group or atom which is present into the plane of the paper. That's the condition we have to satisfy. The least priority must be into the plane, right? So we have to satisfy that condition. So what we do, we'll swap this H and the group which is present into the plane of the paper. That is CH3 in this case. When H and CH3 we swap, so we'll get what? We'll get this molecule. Yes or no? When we swap H and CH3, we'll get this molecule, right? Which is R, correct? Whose configuration is R. First we swap this, find out the configuration. If it is R, and we know this molecule we get by odd number of exchange from this molecule. So if it is R, odd number of exchange we have, so this must be S. Got it? Is it clear? Okay. Now we'll see Fischer projection, how to assign RS in Fischer projection. We have the same thing, all conditions are same. For Fischer projection, the only condition is what, like we have in wedge dash, we have the condition that the least priority must be into the plane of the paper. In Fischer projection, the condition is what? Yes, Arya. When the least priority group is into the plane of the paper, then only you will get the right configuration. You can determine, that's not an issue, but that will be wrong. Okay? Condition we have to satisfy, then we'll determine the RS configuration. Okay? So that's the condition in wedge dash representation. Similarly, in Fischer projection, all conditions are same. We have to assign priority. We have to go 1 to 3rd, via 2, everything. Clockwise is R, anti-clockwise is S. Everything is same. But there we have condition. Similarly, here also we have one condition. And the condition, you write down condition is what? The least priority group, write down the condition in Fischer projection. The least priority group must be on the bottom of the vertical line. The least priority group must be on the bottom of the vertical line. Got it? That's the condition. Now you see in this one, you have to assign RS configuration, this molecule. Suppose we have CH2OH, H, this is Cl, and this is CH3. Tell me the configuration RS. Is it R? Right, it is R. Like priority is what? Chlorine is first, CH2OH is 2, this is 3, and this is 4. So least priority always on the bottom of the vertical line. So here it is present. So we have to go 1 to 2, 1 to third via 2, like this. So it is clockwise, configuration is R. Here also the same thing we have. Even number of swap, configuration remains same. Odd number of swap, configuration will change. Right? Can you tell me what is the configuration of this molecule? Configuration of this molecule, you tell me. C triple bond CH. Then we have CH3. And we have CH double bond CH2. Here we have CH2 CH3. The second one is what? The second one is S. Yeah, right. Whenever you have this kind of ring, a smaller ring will have the higher priority. We have discussed this, how to assign priority in this kind of molecule. If you see that a smaller ring will have the higher priority. So this is 1, this is 2, this is 3, and this is 4. Right? Fourth one is here, and second one is here. So we'll exchange these two. When you exchange these two, we'll have 1, 2, and 3. So 1, 2, and 3 is clockwise. Clockwise is R. So this one will be S. Here you see again, triple bond will have the highest priority. Then we have double bond, and then we have single bond, and then we have only CH3 here. Again, we'll exchange these two. So this one will also be S. Is it S? No, it is not S. It will be R, I think. Right? So 2 here, 3 here. So 1, 2, and 3. It is anti-clockwise S. So this one will be R configuration. Tell me, is it clear? Understood? All of you understood? Any doubt? Okay. Write down the another term. Write down enantiomers. Enantiomers. Definition of enantiomers. Write down. These are the compounds which are non-superimposable, mirror image of each other. These are the compounds which are non-superimposable, mirror image of each other, are called enantiomers. Non-superimposable, mirror image of each other. Okay? Enantiomers are what? Non-superimposable, mirror image of each other. Non-superimposable means what? The molecule okay. Wait just a second. Fine. Next, you write down the next term, or one example we'll see, and then we'll see the next term. Like you see, the example of glyceraldehyde, we have COH. CHO and CH2OH. Now the name of this compound is glyceraldehyde. Write down the name. Glyceraldehyde. This is glyceraldehyde, right? Now the mirror image of this, if you see, mirror image, we are taking the mirror image, that would be this. See, first of all, the bond which is going into the plane and out of the plane, that won't change. because we have mirrored this side, right? We have mirror placed adjacent to this molecule, right? So this two bond will not change. OH will be coming out of the plane. H will be going into the plane. This side we have CHO, and this side we have CH2OH. Right? Now you see this molecule. These are non-superimposable mirror image. Non-superimposable how? You take this molecule and place onto this molecule. The OH will coincide, H will coincide, but this CH2OH will be placed on CHO, and this CHO will be placed on CH2OH. Just keep this, take this molecule, put it over here. Then find OH and H will coincide, but CH2OH and CHO will not coincide here. That's why this molecule are non-superimposable, right? And they are non-superimposable mirror image, hence they are enantiomers of each other. Enantiomers of each other. Got it? Now, can you tell me the configuration of these two molecules? What is the configuration of the both molecules? What is the configuration of first one? Tell me. What is the configuration of the second one? Tell me. Two different answers. Most of you are getting R. Anyone is getting S? Anyone is getting S? Most of you are getting R. R is the right answer. R is the right answer. You see here, again, the first priority is this OH. Second will be what? Second will be CHO. Third will be this. And fourth will be this. So again, it is wedge dash representation. So we have to go 1, 2, third via 2. And this orientation or this rotation is clockwise. So this configuration is R. So when this is R, when you compare this, we'll have odd number of swap here. This must be S. Right? So what we can conclude here, the molecule which are enantiomers of each other, they must have same molecular formula but different configuration. Right? So write down these two. The molecules which are enantiomers of each other, the molecules which are enantiomers of each other, they must have same molecular formula but different configuration. Got it? Understood, guys? Same molecular formula but different configuration. Any doubt? सर 2 मिनट हाँ ठीक है सर okay guys, any doubt? Did you understand this? Wait, Aditya, wait. So enantiomers, if you have to find out, right, what we'll see, the molecule must have same molecular formula but they must have opposite configuration. Correct? This is very important. Now, this molecule, since both are optically active, one chiral carbon, so one will be D, one will be dextro, but other one will be levo, right? We do not know whether this one is dextro or this one is dextro. But if it is D, this one is L. If it is L or if it is D, this one is L. Understood? That we can only decide by the experiment or the rotation of plane polarized light. Correct? So we cannot say that which one is D, which one is L. For that we have to perform the experiment. But one thing is very sure, that if this one is D, this will be L, or if this one is D, this will be L. Right? So they won't ask you the question of dextro and levo, right? But they'll ask you R and S, they can ask you enantiomers. Right? Now these two are optically active compound. So if this rotates the plane polarized light clockwise by some angle theta, this will also rotate the plane polarized light by the same angle theta, but the direction will be anti-clockwise, because one is R, other one is S, one is D, so other one is L. So rotation will be opposite. Rotation of plane polarized light, for this will be clockwise suppose, for this will be anti-clockwise. Angle will be same, right? So when we take the equimolar mixture of these two, right, then that compound is said to be the racemic mixture, right? And suppose we have 10 moles of this and 10 moles of this, then whatever rotation this molecule will bring into the plane polarized light, the same rotation this molecule will bring, but in opposite direction. So eventually the ray will come out without any deflection, and hence the mixture will be what? Hence the mixture will be optically inactive. So this kind of mixture or equimolar mixture, we call it as racemic mixture. Write down this particular definition of racemic mixture. It is the equimolar mixture. Racemic mixture definition you write down. It is the equimolar mixture of the two compounds which are enantiomers of each other. Did you write this? Did you write this? Racemic mixture, it is the equimolar mixture of the two compounds which are enantiomers of each other. Equimolar mixture of the two compounds which are enantiomers of each other. Got it? Any doubt, guys, still here? Any doubt? All of you, answer fast. Anirudh, that is experimental. You have to perform the experiment. Okay, so that you don't have to bother with, because you are not going. They are not going to ask you that question. You have to perform that experiment in the lab. Okay, you cannot do that at home, right? So don't worry with that. Relative things we can say. We can say if this is D, this one is L. If this is L, this one is D. But to know exactly which one is D or L, either you should refer some book, whether the experimental thing is written, or you have to perform the experiment. Right? One last term you write down, that is distereomers. Distereomers are the stereoisomers. Definition you write down. Distereomers are the stereoisomers. Distereomers are the stereoisomers whose molecules are not mirror image of each other. Stereoisomers, or simply you can write down distereomers are the stereoisomers which are not mirror image of each other. Simply that this is better. Diastereomers are the stereoisomers which are not mirror image of each other. Okay, the two molecules which have same molecular formula but they are not mirror image of each other are called diastereomers. Okay, all the geometrical isomers cis, trans, syn, nt, ez are not easy. We cannot say easy. We cannot say. Write down all geometrical isomers in bracket. Write down cis, trans. All geometrical isomers in bracket. You write down cis, trans are geometrical isomers of each other. You can draw one cis and trans molecule which has the same molecular formula. You must see they cannot be the mirror image of each other under any circumstances. Okay, so all the molecules, all the geometrical isomers in bracket you write down cis trans are diastereomers of each other. Second important point, the last point for today you write down, diastereomers can be of any combination. The last point for today, diastereomers can be of any combination. Can be of any combination. Any combination means what? When we explain diastereomers, we explain in a pair, right? For a pair of molecule, we say these two pairs are diastereomers of each other. These two pairs are enantiomers of each other, right? So any combination means what? Both pair or both molecule in a pair can be optically active, right? Both can be optically inactive, or one can be optically active and other optically inactive. Any of these three combinations possible for diastereomers. This, on the basis of this also they have asked question, and the first point that I have given you, geometrical isomers cis trans are diastereomers of each other. On the basis of that also they have asked question. Okay, so any doubt till here, let me know. Let me know if you have any doubt. Right, so we'll wind up the class here. Okay, you can solve the questions of stereoisomerism. It's given in any of the books. I'll share the assignment with you tomorrow, not today. Okay, but you can revise all the things that we have discussed. Each and every line is very important. I have been very specific, right, towards uh, the each and every concept. Okay, so I hope all of you have written all the small concept that I have taught today. Okay, you must revise that. Solve any book. If you have solve questions of stereoisomerism, you can solve those questions. I assume that, right? So I will share the assignment on this, okay, tomorrow. Then you can solve that also. No doubt. So can we wind up the class here? Okay, guys. So okay, guys. We'll see you in the next class. Take care. Bye bye. Thank you for joining.